And we're back for thermochemistry. This is podcast 4.3. So if you're not in unit 4, you better find another podcast. This one's all about enthalpy. So this is nothing new for you. Enthalpy is a state function, and by that we mean it depends only on the state or the condition of the system, not the pathway or the details of how it came to be in that state. So let's have a look at a specific reaction. Here's our reactants, methane and oxygen. Then here's our products, carbon dioxide, water, and heat. This looks familiar, right? Methane gas combined with oxygen, that's what happens in your Bunsen burner. So the graph here shows how the energy changes. The potential energy of the reactants is higher than the potential energy of your products. So your energy went down by this much. If I could draw a straight line, that'd be helpful, but I can't, so I won't. All right, so what do you think happened here? The energy went down. That means it was released from the system to the surroundings, right? This has got to be exothermic. No big surprise, right? It's combustion. Combustion reactions are exothermic. They release a lot of heat and light. This one is like 1800 kilojoules per mole, so quite a lot. Something like that. Anyway, let's look at another one. Here's another reaction. And just as you might have suspected I would do to you, this time we start out with lower energy and the products have higher energy, right? N2, O2 are the reactants and NO is the product. So here the energy increases. Where did it come from? Had to come from the surroundings. We put heat into this reaction. That's why heat is listed as a reactant. So when you're writing an equation, you can put the heat on the reactant side if it's going into the reaction, or on the product side if it's coming out of the reaction. Makes sense, right? Because products are the things that come out of the reaction. So how do we find the enthalpy change? We find the difference in the height of these two lines. So if I give you a graph with lines like this, use the graph, find the difference in height, and calculate delta H. You don't have to know anything else about it. If I give you a graph to read, then the answers are on the graph. It's that simple. Let's look at the next part. So, specifically, what do we mean by enthalpy? Delta H is the sign for enthalpy. This is a thermodynamic function just like delta E, and it accounts for the heat flow in chemical changes that occur at constant pressure. So let's look at that constant pressure idea, all right? I want to make sure that you get this. So just H, not delta H, but just H, depends on the initial amount of energy plus the pressure times the volume, all right? And so that means if we're going to change the enthalpy, we're going to change the energy and change the volume. Does this look familiar to you at all? That's right, it's work. Only remember, work is minus P delta V for a gas because we're compressing or decompressing. And then energy is Q plus W. Look, work again, right? So let's substitute. In the place of energy, I'm going to put Q plus W. And then in the place of minus P delta V, I'm going to put work, which is a minus W, and here's what this equation looks like now. Delta H is Q plus W.
Harrison Mangles, if you're still in the building, could you report to the office, please? Harrison, to the office.
So delta H is Q plus W, Q at that pressure, right? Minus W, minus P delta V. That's what went right in here. And so work just goes away, and all I'm left with is Q. Remember, Q is heat. So enthalpy and heat are the same when our system is at constant pressure. So the change in enthalpy is easy to measure if you can measure the heat of the system that's gained or lost to the surroundings. So let's look at enthalpies of a reaction. Basically, if we're going to use the triangle, what we're talking about is final conditions minus initial conditions, right? So in the final part of the reaction, we have the products. And in the initial part, we had the reactants. So it's the overall heat of the products minus the overall heat of the reactants. That's what we call Hess's law. And so sometimes we just call this delta H reaction. And if we're at standard conditions, then you're going to put a little circle there, right? Like that. And if we're talking about heat of formation, we put a little F there instead of a heat of reaction. So what we know is that where your delta H is negative, then that's an exothermic process because your final value is less than your initial value. And where delta H is positive, that process will then be endothermic because your system gained heat from the surroundings. Let's look at a thermochemical equation. Thermochemical equations are basically chemical reactions that also show the associated enthalpy change. So we call it a thermochemical equation if you have a part here that's the chemical equation, and then a part here that gives the heat, right? And so this one would be, since it's negative, exothermic. Let's do some calculations. Here's a few tips before we get started. Be careful about stoichiometry. You must have a balanced equation or you're not going to get the right answer. And then pay attention to signs. The sign of your enthalpy change is opposite if you change the reaction around. If you reverse the reaction, change the sign of heat. Right? We learned that last year when we did Hess's law. And then pay attention to the state of matter. Some heats, especially in heats of formation, will have a different value for liquid than they have for gas. So watch, like liquid water and water vapor have two different delta H values. All right, let's do a problem. So here we go. We have a reaction of burning magnesium. We've seen that one before, and that one should release energy, and indeed it does. That's a negative delta H. So hey, now we know the answer to part A. Is it exothermic or endothermic? You got it. Exothermic, because that delta H is negative, and it is a burning, right? So we're releasing energy to the surroundings. Now we're going to calculate the amount of heat transferred when 2.4 grams of magnesium reacts at constant pressure. Well, I sure hope you know the drill by now. You know, when in doubt, we go to moles. So we're going to start with 2.4 grams of magnesium, and we're going to change this to moles of magnesium. So 1 mole of magnesium, get your periodic table out. I gotta get mine out. Luckily it's right here on top. Okay, magnesium has a mass of 24.31 grams. That's easy math, right? And then in our balanced equation, we get 2 moles of magnesium making this much energy. So I need to have moles of magnesium where it will cancel. 2 moles of magnesium corresponds to a negative 1204 kilojoules. All right, we're ready for the calculator. So 2.4 divided by 24, you should know about what that is. Got to push the right buttons to get the right answer though. And then we're going to multiply by negative 1204 and then divide all that by 2. So I get negative 59.4 kilojoules. How many sig figs do I get to keep? 2. So we'll drop that off. 59 kilojoules, negative 59 kilojoules, it is. So that's the amount of heat transferred when you burned 2.4 grams of magnesium. We burned way less than 2.4 grams last year in class. Let's look at part C of this problem. So this part asks how many grams of magnesium oxide are produced during an enthalpy change of negative 96.0 kilojoules. So again, we're going to go to moles. We know we have negative 96.0 kilojoules to start off with. Then in our reaction, how we get to moles here is using this. This corresponds to this balanced equation. So we know that there's negative 1204 kilojoules for every 2 moles of magnesium oxide. And I get that number 2 from the stoichiometry of my balanced equation. All right? So now are we done with the question? I've got moles of magnesium oxide. My target says grams. So we're not quite done yet. Every 1 mole of magnesium oxide is how many grams? Let's see, 24.31 plus 16. So, oh, I subtracted 16. I don't recommend doing math that way. How about 40.31? Duh, I did not need a calculator for that math. See, there is an example right there of a calculator dependency problem. Gonna have to form a support group for our calculator dependency, huh? So, after all my calculations, this is what I get, 6.428 grams, and I'm gonna keep, looks like 3 sig figs. So 6.43 grams of magnesium oxide is formed when we get an enthalpy change of negative 96 kilojoules. All right, that's how you do it. When in doubt, go to moles. We're still following that same advice. How about that? Been good advice. Gets us a long ways. Now, our next part, how many kilojoules of heat are absorbed when 7.5 grams of magnesium oxide is decomposed into magnesium and oxygen. All right, so now we're going backwards, right? We're going to take magnesium oxide and break it apart into magnesium and oxygen. So we've got to balance this equation, and we know the associated enthalpy change, since I reversed the reaction, is a positive 1204 kilojoules. So far so good. Since we reversed it, we got to change the sign of our heat. Now let's get working. 7.5 grams is what we're going to start with, grams of magnesium oxide. And that molar mass was 40.31 grams of magnesium oxide for every 1 mole. Okay, let's look at our balanced equation now. We know that 2 moles of magnesium oxide is going to correspond with 1204 kilojoules of heat. 1204 kilojoules. And that's positive now because we changed the reaction. We're going in the reverse direction, right? So let's see, grams canceled, moles canceled, and I'm left with kilojoules, and that was my target. So I'm ready to reach for my calculator. 7.5 divided by 40.31, and then multiply by 1204. And I got 224, 3 sig figs will do, kilojoules of heat was absorbed in order to decompose my magnesium oxide. So that's how we're going to work with problems about kilojoules and thermochemical equations. Don't make it harder than it needs to be. Really, it's just a T table. Go to moles, you'll be fine. All right, see you next time.